And I want this variety to have an isolated singularity just in the origin. And it's supposed to be log terminal. Moreover, I would like to have an algebraic torus acting on my affine variety. So C star to the k, where let's say x has dimension equal to d. And let me denote this torus by t. I'm going to assume that the action is linear, so it's given by a set of weights, let's say u1 up to un, sitting in the character lattice of the torus, which I denote by m. Okay, to this data, I associate the weight cone. So it's just the positive span of the weights. This object lives in the associated real vector space. And I'm actually more interested in the dual cone to this cone, which I denote by sigma. So this sits in the dual of this one, which I denote by nr. Okay, now I would like to associate an additional object to this variety. This is called a polarization or a Rape field. And this is simply an element in the interior of the cone sigma. And for the moment, let me assume that this choice or this choice of psi is made in a way that it's integral up to scaling. So I can rescale it to an integral vector. Or in other words, it spans a rational subspace. Okay, so our data now consists of our Fano cone singularity and this extra data, which I call the polarization. And my first aim is now to associate two compact algebraic, compact geometric objects to this data. And the first way to do this is as follows. So I mean, picking an integral vector here just means we are picking a one-parameter subgroup of our torus. Right? And so in particular, I obtain a C star action on X. So and the origin is going to be a fixed point, so I may exclude the origin, and C star still acts on this subset. And what I'm going to do is I'm just taking the quotient under the C star action and obtain a projective variety. And since I assume that that I have an isolated singularity, it means once I take away the singularity, I'm going to be smooth. So downstairs here, I'm only seeing quotient singularities. So in other words, what I obtain is an orbifold, and it's going to be projective, so I can see it as a scalar orbifold. And because I assume that the singularity is log terminal, what I get is actually Fano. Yes. Yeah. Yes. So I want this to be full dimensional and the dual cone as well. Yeah. Okay. Good. So this is very classical, and you are probably used to this way of associating geometric object in this way to this data. But there's another one which I would like to talk about. And what I could do instead is I can take the intersection of x with the unit sphere in my complex vector space. And this is called the link of the singularity. And this is going to be a manifold of a real manifold of dimension 2D minus 1, real dimension, because I'm intersecting outside the singular locus. Okay. And the important point here is now that this comes with some additional structure. So it's more than just a smooth manifold. So first observation is, of course, the action of the algebraic torus does not survive this intersection, but what survives is at least the action of the compact torus. Right, so if I start with a point on the unit sphere and act by an element of the compact torus, then all the coordinates have absolute value equal to 1, so it doesn't rescale the length of the vector. Okay, so this is the first observation. Second observation is actually the choice of psi has a meaning here. It can be interpreted as a vector field on L. And check. Yeah. And there comes even more structure. So somehow here I stressed the point that we obtain a Kähler orbifold, so there's a Kähler metric, and I would like to see something similar in this situation, and indeed I get something similar. It's called a Sarsakian metric. And I'm not going to define what this actually is, but I'm giving some properties which help to match up what's going on the left-hand side and on the right-hand side. Okay, so let me just pick one property of a Kähler matrix. I mean, first of all, it's a Hermitian matrix, so we want it to preserve the complex structure. So we want to have an equality like this. And I will explain a little bit, at least the corresponding property on that side. Okay, so let me start in the naive way and just copy what I've written here, and then discuss the problems with writing down such a statement. Okay, I mean, so first of all, I'm talking here about the complex structure. So what should the complex structure on L be, right? So, I mean, at least there's a complex structure around. Just if I exclude the origin from X, I see a complex manifold. And so I have a complex structure acting on there. But certainly, this is not going to preserve the tangent space of L, right? The tangent space of L simply has the wrong dimension to be preserved by a complex structure. But there's a subspace or a subbundle which is preserved. And this gives me a hyperplane bundle inside the tangent bundle of L. So let me write just intersection of TL with JTL. And so this is preserved by the action of the complex structure. So here such a statement makes sense. And this gives you essentially what's called a contact structure on your manifold. Okay. And somehow we want everything to behave or to be compatible with the choice of this vector field. This is the next ingredient here. So we want psi to be orthogonal to this hyperplane bundle, of course with respect to the chosen metric. And I want it to be normalized with respect to the metric. And there are more conditions essentially corresponding to the closeness of the corresponding form. And I'm not going into details now. Okay. So we have these two different constructions. And the next observation is that they are actually closely related to each other. It's not hard to see that the link is an S1 bundle over this projective variety of Kähler orbifold. How to see this? Let's pick a C star orbit upstairs here. This goes down to a point here by definition of a quotient. On the other hand, intersecting a C star orbit with the unit sphere gives me just an S1 orbit. Okay? And this is the S1 orbit which sits over the point here. Okay. And yeah, I mean, this should just give you an idea why there's a close relation on both sides. And this close relation actually helps you to solve certain geometric problems on one side by solving the corresponding problems on the other side. Yeah.
So maybe what in orbifold has one side of that?
Yes.
Not the hyperplane.
Yes. So yeah. So what I so the next point I want to make is that the geometries on both sides are closely related to each other. So in particular, somehow the choice of a Kähler-Einstein metric on one side induces Sasaki-Einstein metric on the other side. And vice versa, so both properties are equivalent to each other. And this was actually an important point to actually construct Sasaki-Einstein manifolds. So Koller did a lot of work on this by using exactly this correspondence. So constructing Kähler orbifolds used methods available on this side to prove that they are Kähler-Einstein, and then deduced that there is a Sasaki-Einstein metric on that side. And so, yes, I mean they are somehow I would say the fathers of this theory. Yeah. But I mean, to do this with orbifolds, I think this is due to Koller, if I remember correctly, instead of manifolds, just manifolds. Okay. Good. So now I'm changing a little bit my preconditions here. I'm dropping this very essential condition upstairs. So now I'm allowing also irrational choices for psi. And then the Sasakian metric which arises in this way is called irregular. Okay, and the main point of this talk is that now the left-hand side breaks down. So there's no left-hand side anymore. So there's no C star action coming from a irrational choice of psi. So this goes away. Okay, and one question one can ask is, given x and xi does, for this choice, the link together with this vector field admit a Sasaki-Einstein metric. I mean, this question is interesting in general, but in particular, we're now interested in the situation that xi was an irrational choice, because then somehow we have lost an important tool. Okay, and one idea to somehow save the situation for algebraic geometers is to work with the affine variety instead of the projective variety downstairs. Okay, so there's still an approach via algebraic geometry to study this situation. And let me maybe first give an example just illustrating what happened here in the toric case. So which just means that k is going to be equal to d. Okay, and we start with a nice situation. So we start with the left-hand side when it still exists, and we pick a simple toric Fano manifold by giving a polytope P. And in this case, this is just going to be the projective plane. And in the polytope, the origin is included. And now I'm looking at the corresponding cone singularity, meaning I'm looking at the affine cone over this projective variety. And in the toric language, this is given by embedding now the polytope in vector space one dimension higher, and I'm going to embed this at level 1. And take the cone over it. Right, so I take P, embed it in level 1 in the vector space and one dimension higher, and the origin here becomes a distinguished point inside this constructed cone here, which I denote by U. And yeah, I mean, this is now describing, or let's go to the dual cone. So this cone plays the role of omega sitting inside MR. Let's look at the dual cone. Sigma sitting in NR. And so U here was just the origin raised to height 1. And here I can make a particular choice for xi, doing the same thing. Xi equals 0 raised to height 1. And now my x is going to be the toric variety corresponding to this cone. And the question is, if I'm now I'm in the setting like here, so now I'm picking psi exactly in this way. So this gives me a C star action corresponding to the one parameter subgroup I have just picked. I can take the quotient, and this just brings me back to this polytope, to the toric variety corresponding to this polytope. Okay, you can paraphrase this in this toric language. So let me first fix the fact that I have chosen xi inside the hyperplane where u is equal to 1, and u I have chosen in the hyperplane where xi is equal to 1. And now I can recover P just by taking the intersection with the cone of the cone omega with the hyperplane where xi is equal to 1. Okay, so this works with the choice of xi, which I've just made, but it also works in exactly the same way if I'm now moving psi to another, let's say, rational vector for the moment, right? So, and I'm going to pick another psi on this hyperplane again. So what happens now, the hyperplane which I'm using to intersect with is just this hyperplane, but I start to tilt it, right? Where this is a fixed point of the tilting. And if I make a rational choice here, the intersection is going to be a rational polytope, and I can still associate a toric variety to this situation. So everything works well if I make a rational pick or a rational choice for psi. Once I'm choosing an irrational vector psi, my polytope is going to be irrational, and I still get a nice polytope, but no way to associate a toric variety to it. Somehow this explains exactly the problems on the left-hand side here. Okay, so the question is now how to decide about whether for such choices Sasaki-Einstein metric exists. I mean, in this situation, we can still make use of this correspondence, right? So we know that a toric variety, projected toric variety, admits a Kähler-Einstein metric if the barycenter is equal to the origin in this picture. Okay, and I can just translate it to the other side. It just tells me here that I get a Sasaki-Einstein metric if and only if this intersection polytope has barycenter equal to this distinguished point upstairs here. Okay, and with the same argument, this works for every rational choice of psi, right? So we just don't know what happens if I pick my vector psi as an irrational vector. But one has a strong guess now, right? So probably it's exactly the same condition as for a rational choice. And this is indeed true, and this comes from results first given by Martelli, Sparks, and Yau for one part of the theorem, which I'm going to write down in a minute, and the other part is due to Futaki. Oh no, wrong. And the first part says that if my manifold admits a Sasaki-Einstein metric, then psi, this vector field, minimizes the volume of my manifold. Right, so the way to think about it is a choice of psi somehow restricts the metrics which I'm allowed to choose, and as it turns out, the volume only is only dependent on psi, not on the metric itself. So at least the statement makes sense. So I'm looking for minimizers psi of this volume functional. Okay, and the second condition, the second part of the theorem tells me that if X is toric, then also the converse is true. So nowadays both parts follow actually from the work by Collins and Sakaidi, so which were able to prove a version of showed that the existence of Sasaki-Einstein metric is also equivalent to some notion of K-stability for this affine variety I started with. Okay, so let me now show what this means maybe in a little bit more complicated situation than this one. So let me look at the blow-up situation. So I start now with the blow-up of P2. This means the cone here changes a little bit. Now it looks like this. Right, and if I claimed that or in the situation before, the barycenter was equal to the origin, now it certainly moved somewhere over here. Right, so the barycenter is not anymore equal to the origin, so I'm not getting a Kähler-Einstein metric on this side, and equivalently, I'm not getting a Sasaki-Einstein metric on that side, because the barycenter is there. Okay, but now I might ask, maybe just the choice of Xi was the wrong one. Let's play around with the Xi here. And I'm moving on this hyperplane, I'm going to move my choice of Xi. As I said, what does it mean? If I move in this direction, I'm going to tilt this hyperplane, but leaving this fixed. And actually, there's a whole line being fixed. And I mean that the barycenter is on this side just tells me that most of the volume of this polytope lies on this side of this line. Now I'm going to tilt, and if I'm going to tilt this part down in the cone, it becomes smaller. Right? So if I'm tilting something down in the cone gets more narrow towards the origin. So I'm making this part smaller, and I'm making this part larger. This means the barycenter is going to move in this direction. It's not hard to see by continuity that at some point it will hit this point. So there is a choice of a Xi here, which allows us to choose a Sasaki-Einstein metric on there. And the point is, this happens exactly, or in this case, actually in an irrational situation. So I have to choose Xi to be irrational in this example. So this gives me an example. And actually, it's the first example of an irregular Sasaki-Einstein metric. And this is due to, for authors, Gauntlet, Martelli, Sparks, and Waldron. And this was a bit of a surprise because people maybe suggest or believe that such an irregular Sasaki-Einstein metric might not even exist. So this was a surprising result. And if you look at this example a little bit closer, you can actually determine what L is in this case. So L in this case is S3 times S2. And you can cook up similar examples for connected sums of this manifold. Again, toric examples. Okay, so I can do the same thing essentially for connected sums. And by a result of Koller, we know that we have to look for irregular Sasaki-Einstein metrics only on those guys, and as the last remaining possibility on S5. Okay, so there could be for simply connected manifolds. So it's a natural question arising from these examples. Whether there exists an irregular Sasaki-Einstein metric on S5. I mean, in dimension 5, these are all the possibilities. Those 1 and S5. Okay, and so my contribution to this is the following theorem. So giving a negative answer to this question, namely there are no irregular Sasaki-Einstein metrics on Q homology 5 spheres. Okay. So sorry? The possible types are for Q homology 5 spheres. I'm not sure. Yeah, the only thing I know is if you ask for simply connected, then it's only those and S5. Yeah, so in the book of Boyer and Galitsky, there's a comment on this. Yeah. Okay, so let me just start to discuss a little bit the proof of this theorem. So let me review the situation we are in. So the dimension of L has to be 5, but on the same time this was 2D minus 1 of the complex dimension of X, right? So this implies that we are talking about affine varieties of dimension, complex dimension 3. First of all, then what's the dimension of the acting torus? So, I mean, I'm assuming an effective action. So this means the possibilities are 3, 2, or 1. But somehow the case that the acting torus, the maximal torus has dimension 1 can be excluded right away, because, I mean, if I'm looking for something irregular, this means I'm looking for a vector in the vector space which I can't rescale to an integer, but in a one-dimensional vector space I'm always able to do this. So there's no question in this case. I have to be quasi-regular, so I can't be irregular in this case. So I have to consider these two cases. And let me talk most of the time about this case. It's a toric case, and if there's time, discuss actually the hard case is this one. Okay, or the harder case. So toric case. So this means K is equal to D. And there's something else we know, right? So we are talking about a Q homology sphere. So I know something about the cohomology of L, And the only thing I'm interested in is actually the second. And this can be seen to be the same as the cohomology of X with the origin removed, because it's not hard to see that this is a deformation retract of this one by just rescaling every vector to length 1. Okay, on the other hand, this is equal to the class group of X. So if I want this to be torsion, in other words, what I know is that X is Q factorial. So we are talking about a Q factorial toric variety. So this means that X is actually a toric variety corresponding to a cone, and the cone sigma is spanned by exactly D integral vectors. Where those form a basis of the vector space. Okay. So it's just a simplicial cone, in other words. Okay, so I'm talking about a simplicial cone. And now we consider the action on this vector space induced by permuting just these basis vectors. Okay, so I mean, by the choice of this action, it preserves my cone sigma. It also preserves the volume of this intersection polytope. I mean, so it's essentially, this action is induced by a permutation matrix, a matrix of determinant equal to 1. And the same holds true for the dual vector space where this lives in, so it doesn't change the volume functional. So once we know that there's a unique minimizer of the volume functional, it follows that this choice of psi has to be invariant under this permutation. But I mean, in particular, I can write psi in this basis. So what does this mean now to be invariant? It means just that permuting the coefficients give me the same vector. In other words, all the coefficients are the same. Okay? Yeah, so this means the minimizer has to have this form, but this vector, I mean, all these vectors were assumed to be integral, so the sum of these vectors is going to be integral as well. So in other words, psi is just a rescaling of an integral vector, implying that I can't have an irregular Sasaki-Einstein metric in this case. Okay, now I have 50 minutes left. Is that correct? Or, yeah. Okay, so then let's now talk about the remaining case. So now, yeah, just a remark. I mean, here I didn't have to use the fact that I'm in dimension 3. The same argument works for every toric. And this was probably known before. But it gives me a good idea what to do in this situation now. So now D is still equal to 3, but I'm looking at a torus of dimension 2 acting in this situation. And this situation is often called situation of a complexity 1 torus action. Complexity 1 because the difference of these dimensions is 1 in this case. So this is complexity 1. Okay. And the important point for you to know is only that in this situation, I also have a combinatorial classification of these affine varieties, which is close to the combinatorial classification of toric varieties. And many properties can be read off from this combinatorial description. So actually, the upshot is I know a lot about these varieties. So we are looking now for a variety of affine variety of dimension 3. Torus acting, the acting torus has dimension 2, and we want it to be still Q factorial. And to have an isolated singularity. And what I get from this is even more information about the object I'm looking at. And from all this information, it's possible to construct a further degeneration of this variety to a toric variety. And I should add here, so it's an equivariant degeneration of the object I'm looking at. So in other words, I'm having a family sitting over C, where the general fiber is the complexity 1 variety, affine complexity 1 variety I'm starting with, and the special fiber is going to be a toric variety, which I denote by X prime. So, and again, because of all the input we have, we actually know a lot also about this X prime, which I'm going to use. So, our construction gives us, again, a Q factorial toric variety. And as such, I can write it, or can look at the corresponding cone. And I denote this cone by sigma prime. So I told you that I'm looking at equivariant degenerations, yeah? Yeah, so this really comes from this construction. So I can construct so from the input data, I can construct a degeneration to a Q factorial toric variety. But for example, I don't know whether this works in higher dimensions. So in this case, I can just show it's Q factorial.
So you assume the topology of the
Yes. Yes, this again. So I assume that X is Q factorial, but it wouldn't be clear to me why X prime has to be Q factorial, but via this construction, what we get is Q factorial.
So you mean there exists
Yes, there exists such a construct. No. Yeah. Okay, and being equivariant means we still have the action of t here, but we also have an action of an additional C star component. Let me denote this by T prime. Okay, so we have, in particular, we have an embedding of T into T prime, and this gives me an embedding of the corresponding vector spaces nr into the corresponding vector space n prime r. I mean, which is just the vector space over the lattice of one parameter subgroups of T prime now. Okay, and I mean, I told you inside here now sits sigma prime, and inside here we had our sigma, and sigma is just obtained as the intersection of sigma prime with this subspace. Okay, so I'm drawing a picture right now of this situation. So we have our simplicial cone, sigma, spanned by three vectors. Let me call them v1 prime, v2 prime, v3 prime. And now there's a subspace of this three-dimensional vector space which corresponds to the vector space nr of our original two-dimensional torus. So this intersects this cone somewhere over here. Right, and the intersection is again a cone. Maybe colored chalk. Okay, and this intersection, this was the large cone is sigma prime, and the intersection with this subspace and R is my cone sigma. Okay, and Xi sits somewhere in here. Right? So I have to solve again my minimization problem. I have to calculate the volume of the link with respect to this choice of Xi. The question is, how can I do this in this situation? And somehow it turns out that this volume behaves well with respect to degeneration. So I can actually calculate the volume on this toric variety in the special fiber. So this just gives me the same formula as before. This is just the intersection now of the polytope P prime for this choice of Xi. And I have to solve this minimization problem. And a first naive idea would be just use the old argument. Right? So everything looks like in the toric situation. I have to minimize my choice of Xi. I can look for the group given by permuting v1 prime, v2 prime, and v3 prime. This leaves this cone sigma prime invariant and apply the old argument. But actually, my minimization problem is different now. I'm allowed to choose my Xi not in the whole cone, but only in this small cone on this hyperplane. So I have to solve a different minimization problem. And somehow the whole situation now is not invariant under this big permutation group. But as it turns out, and this is again special from the degeneration I have constructed, it's still invariant under just swapping v1 prime and v2 prime. And now I can apply the old argument because, I mean, now I'm looking only on this smaller cone. This claim was that under this action induced by permuting V1 prime and V2 prime, the smaller cone is still preserved by this action. So, and you can see what it does on the smaller cone. It gives you the action induced by permuting this generator with that generator, and you just do exactly the same argument as before. So if you call this generator here V1 and this V2, then it follows that psi has to be chosen to be some rescaling of just V1 plus V2. And these two are integral vectors, so the sum is an integral vector. So psi is again to be up to rescaling an integral vector. And this leaves me with the conclusion that also in this case of complexity 1, I cannot have a irregular Sasaki-Einstein metric. And in dimension 3, I only have to consider complexity 0, which is the toric case, and the complexity 1 case, which I just did. So I'm done for dimension 3. Okay. And this is all I wanted to say.